Learners, global trends of population growth, urbanization, and rising living standards are increasing the demand of water, food, and energy. Uncertainties associated with the climate change further complicate these interconnections and add another dimension to it. Water and food security are the key challenges under the climate change, as both are highly vulnerable to continuously changing climate patterns. The impacts of climate change on the global hydrological cycle are expected to vary the patterns of demand and supply of water for agriculture, the dominant user of fresh water. Due to small shift in the seasonality and water availability, the extent and productivity of both integrated and rain-fed agriculture can be expected to change. It is predicted that the portion of the land used to cultivate our major crops such as wheat, soybean, rice and maize in some countries would witness permanently drier conditions, whereas in others similar land proportions would face permanently wetter conditions from climate change. It is projected that the tropics and the north would become wetter, while parts of Africa, Americas, Australia and Europe would become drier. Countries like Mexico and South Africa would receive less precipitation. However, in India, the entire land dedicated to rice cultivation, 91% of the land for maize and 80% of the land for soybean would face wetter condition within the next 40 years. Overall, the climate change drivers such as increased rainfall, drought and flooding coupled with the higher temperatures will impact the cropping patterns and overall crop yields and may offset the global food trades. Now, with this, let us see where we stand in this nexus of water, food, energy, and climate change. A nation's water footprint is defined as the total amount of water needed to produce goods and services calculated by adding all the water consumed plus water inherent in products imported, then subtracted by the water in exports. India's water footprint is 980 cubic meter per capita. While India ranks below the global average of over 1200 cubic meters, its 1.3 billion people collectively account for over 12% of the world's total water footprint. The Indian agriculture sector contributes significantly to this water footprint. India is one of the world's top producer of cotton, rice, wheat and sugarcane. All these crops require substantial amount of water to cultivate. In India, the Green Revolution of 1960s helped to ensure food security for the starving population. However, the economic of crop pricing and market associated with the Green Revolution has damaging and far-reaching consequences on the country's water, energy and land resources. The genesis of India's unique energy irrigation nexus was the policy decision in many states to supply unmetered power to the agriculture sector. It coupled with the deep dependency that farmers now have on groundwater for irrigation and the energy subsidies which help perpetuate the dependence makes India's case rather unique. In the module on irrigation in India, you have learned that India holds most extensive irrigated land globally and over 65% of it is irrigated using groundwater. Post-Green Revolution, groundwater use in irrigation has grown faster than in United States, China, Mexico, Spain, Pakistan, Bangladesh and Iran. Many factors explain this extraordinary rapid growth in groundwater usage. However, arguably, the most potent factor explains why groundwater irrigation grew faster in India than elsewhere in the regime of flat rate tariff and power subsidies that India has evolved to support groundwater irrigation. To support the agricultural sector, currently central and state governments provide various types of subsidies. It includes input subsidies, price subsidies, infrastructure subsidies and export subsidies. The annual central government subsidies to farmers amount to over 1,20,000 crore per year. Almost an equal amount of subsidies are granted by the state governments annually. Overall, farm subsidies amount to 2 to 2.5% of India's GDP. Compared to global electrical consumption in agriculture, India's power use is quite exceptional. Total agricultural electricity consumption in India outstrips comparable countries such as China, US, Russia, and Brazil. Electricity consumption in agriculture increased from 3% in 1947 to 27% in 1997. Subsequently, it reduced and currently account for 18% of the total energy consumption in India. This high electricity consumption in India is a manifestation of intensive groundwater irrigation. Let us now have insights into the net virtual water flows of some of the prominent countries, and we'll see where India stands in it. China, Brazil, and India are also top virtual water net exporters, mainly because these countries' economic growth is driven by exports of goods to developed countries, thus export of large amount of virtual water. When looking at the ratio of water withdrawal versus water availability, India and China extracts 32% and 20% of their water availability respectively. Therefore, the large amount of virtual water export from these two countries may impose significant pressure on their own water resources and ecosystems. The net virtual water flows among the different countries is shown in this figure. It is evident that the European Union as a whole receives a considerable amount of water from all over the world, including developing countries such as China, Brazil, India, and developed nations like USA. India extracts more than 30% of its available water, and it is the second largest virtual blue water exporter, mainly exporting to the European Union, which is generally not water scarce. Brazil is ranked as the top virtual green water exporter, and its virtual green water exporter is more than twice the amount of virtual green water of the second largest exporter of India. It means that India exports 39 billion cubic meter of the virtual water on an average per year. Rice is the highest exported food product, followed by buffalo meat and maize. India prominently exports less water intensive crops. Hence, the virtual water trade is not balanced in favor of India. In 2019 alone, agricultural export generated a revenue of 1.29 lakhs crore for India, a sizable share. However, these exports need to be monitored for sustainability with the effect of climate change factored in. Effective irrigation techniques, irrigation scheduling, suitable crop selection based on climate conditions, soil type, water availability, and using alternative water sources for irrigation could help reduce groundwater consumption. Let us summarize this lecture. For achieving various targets of Sustainable Development Goals 2030, we require to reduce hunger and eradicate poverty in a sustainable manner. For this, we have to achieve security for water, food, and energy simultaneously. It could be only done by improving the overall resource use efficiencies and link the production and consumption patterns. In this regard, the Nexus approach distinguishes the interconnections of natural resources and aim to balance the various goals and interests to be achieved with the limited resources. The water, energy, food nexus is about understanding and managing these often competing interests while also ensuring the integrity of ecosystems. Hence, the Nexus approach advocates for more sustainable use of our natural resources. This widening water agenda requires an approach addressing issues between sectors, countries, regions, and stakeholders, where it is vital to identify and name the most critical barriers and obstacles and exploit opportunities. In such a effort, water will be the medium by which we should address this nexus. Thanks.